Hi, my name is Antoine Dumont. Today I'll talk to you about organized photo-induced nanostructures in AS2S3 class. I was supervised by Sandra and Sadek with the help of Mohamed El Amaroui. I work for the research group of Younes Sadek, who is the holder of the Canadian Excellence Research Chair in Photonic Innovations. So my outline, I'll talk to you about the motivations for my project, the state of the art, also different parts in my experiment, also the perspective for future and current work, and my conclusion. So the motivations. In the research group, some observations were made of unorganized structures photo-induced by femtosecond laser on the GAS class, germanium and sulfur compound. So we wanted to explore more specifically that kind of structure in a AS2S3 class, which has a different molecular structure. Also, the fiber drawing parameters for the AS2S3 are really well known in the research group, so we wanted to try to inscribe directly some gratings on an optical fibrous cross-section. The objective was to understand and control the formations of nanogratings on that type of glass, and some different applications. There's the most important one is a new ultra-sensitive pressure sensor with the optical fibers, and also some development in optical memory technology. So the state of the art, here we can see some studies about nanogratings in silica glass, which is the most often used glass in that kind of studies. Those gratings were inside the glass, so the research group needed to polish a lot of glass to get to the structure. A more recent study obtained the same kind of structure, which is a groove structure instead of ripples like we obtained in my project, but the structure was at the surface of the glass. This is the first attempt on chalcogen-like glass, which is the family of glass of the arsenic and sulfur compound. It is on the surface, and the nanograting structure is perpendicular to the electric field of the femtosecond pulsed laser, as you can see here. The different theory models for the formations of the gratings is not really clear. Basically, the idea is that the plasma created by the pulsed laser interact with the electric field of lasers. So there's a periodic structure created in the plasma, which create the gratings of on our glass. You can see here a few parameters different from the chalcogen glass and the silica glass. You can see, most importantly, the glass transition temperature, which is way lower in my glass. So the work will be a bit different for different thermal treatment and the ablation rate on the glass. So my project, I used samples that I cut from a preform big cylinder of glass, basically, made by Mohamed El Amaroui. I cut it with a width of about 4 millimeters, and I polished them with, to a finish of 1/8 of microns with diamond suspension. The laser used is a femtosecond pulsed laser with pulses of 100 femtoseconds with a frequency of kilohertz. Samples were put to a distance of 46 centimeters, so the beam radius was 0.5 millimeters. So here are a few examples of exposures. We start with short time and low power levels, and go all the way to high power levels with a long time exposure. So the formation conditions for nanogratings, we started, our first tries were with short time and low power. So that's our spot we obtained. You can see that the center is filled with the gratings, the grating, which is vertical. So our laser is polarized vertically, so this level of grating is parallel to the polarizations, which is different from the previous studies. But there's, on the border of the spot, there's crossings between horizontal and vertical gratings. So we saw that there's two levels of grating formed with our glass. The nanostructure's height is about 77 nanometers with a period of 750 nanometers. Especially in the center, the gratings are very well defined. Well, the middle range power is a bit similar, except that the center is all melted, and there's only a big region of crossings between horizontal and vertical gratings. On the border, there's three regions that represent the crossings I just told you about. With a high power at a short time, it is the same kind of spots, except there's a big height difference between the horizontal and vertical grating. This was not visible at low power, and because of the really tiny structure we obtained, I didn't measure really the height difference because it was real difficult to point the exact region where that happened. For a long time exposure, the center is still melted, but there's only a big region of horizontal grating. But the height is a bit higher, but it is not really usable in optical fibers that I'll try to obtain. I'll try to obtain gratings on my optical fibers after that. With high power, there's only a big melted spot with a lot of ablation residues, as you can see here, and there's no significant region of grating. So as summary for the different conditions, you can see here it is the ideal parameters.